So can we discuss quantization a bit?
Sure. Any specific question that you have related to quantization?
Yeah, so in quantization process, like we will be converting the Poissonian brackets to commutator relationships, right?
Yeah.
And also we are just imposing some of the classical functions as ladder operators. So I was bit physically confused of what it mean to shift the classical operators to classical functions to the operators.
Okay.
Yeah.
Let me start sharing.
And yeah, and other doubt is like for especially for the Klein Gordon field,
Yeah.
we will be finding the Hamilton for in the terms of ladder operator which are independent. But if you look at the formulation of the field fundamental itself, you will be finding that the potential is made in such a way that if one of the point is higher than the other point in the field value, then potential is formulated in such a way that this other point also increases for this q of I plus 1 minus q of I whole square, that potential term. So, but if you look at the Lagrangian in the terms of ladder operator, you will get that each and every spring system is non-connected. But we have fundamentally improved the potential in such a way that one point will be influencing the value of the other point. So, how that could be?
Okay.
Actually, I got plenty of doubts, so many doubts, but we'll go slow.
Sure. So I'm not in the institute, so I'll keep my video switched off in order to preserve bandwidth. Okay. We'll start. So okay, so the Hamiltonian that we are getting after the quantization of the real Klein Gordon field is as follows. It's d3p divided by 2 pi q right?
Yeah.
Now, sorry, I think there is 1 over square root 1 over 2 EP as well, if I'm not wrong. Let me see.
I don't think it will be 1 over E, it will be like
sorry,
EP of.
it's not 1 over 2 EP, sorry. It's omega p. So you were saying when we wrote down the Hamiltonian density, it was half pi square plus gradient of phi square plus m square phi square. Now you are saying here we had interaction between phi with its neighboring point through this gradient of phi.
Yeah.
action, but here all these are being independent, as if we are having one simple harmonic oscillator corresponding to each momentum mode P. Right? That's your question. Did I get your question correctly? So, and the Hamiltonian is then d3xh. Now, in order to arrive at this Hamiltonian, so we wanted to quantize the real Klein Gordon field. Now, how do we do that? So we took the Fourier transform of the dynamical variable phi, which is a classical field. So when we do that and substitute it in the Klein Gordon equation, so it was exponential I e dot x, then phi, the Fourier component. If we substitute this in the Klein Gordon equation, del mu plus m square phi, what do we get? We get plus mod of p square plus m square acting on phi. You are clear from this step to this step? So what do we have now? In the momentum space, as if we have, this is minus, call it omega p square phi, where omega p is square root of mod of p square plus m square. So in terms of these Fourier modes of the dynamical variable phi, we have one harmonic oscillator for each momentum mode p, and you can see that there is no interaction between a mode p and another momentum mode, let's say q. So it's like infinite number of harmonic oscillators, each with a different momentum p. You can recognize this with simple harmonic oscillator equation, right? X double dot equal to minus omega square x. That's a simple harmonic oscillator. So there x is a dynamical variable, or the degree of freedom. Here phi is our degree of freedom. And when you write down your field phi in terms of these Fourier modes, the Klein Gordon equation actually boils down to an infinite number of harmonic oscillators, one with each momentum mode p. And that's why when you obtain your Hamiltonian, after writing this dynamical variable so what do you do in quantization? Just the way we do in classical mechanics. Classical mechanics, we had the generalized coordinates qi, qj, and corresponding conjugate momenta pk. We first make them operators, and then we write down the commutation relation satisfied by those generalized momenta and coordinate, which is I h cross delta jk. With h cross equal to 1, it's just I delta jk. So in the same way, to quantize the real Klein Gordon field, what we do is the dynamical variable phi. So so we lift it to an operator phi hat, let's say, and the corresponding conjugate momenta pi becomes an operator, and then we write down the canonical commutation relation satisfied by these two operators. Which is I. But now since these variables are continuous in space, we need a delta function, three-dimensional delta function, x minus x prime.
Yeah, here actually I have some other problem in understanding. Here, basically, you said the Poisson, like one of the thing is like Poissonian brackets are converted into commutation relationship, right?
Yeah,
While for convert in the process of quantization.
yeah.
But like and I don't know Poissonian brackets. So before I started the course, I have no idea on Poissonian brackets. So I started searching a bit. So what I have understood is, so think of like if you have two dynamical variables A and B. Now Poisson in brackets gives a value where based on the change of A, what is the impact on B? That is basically a Poisson in brackets of idea. So it gives a relation between dynamical variables.
Yeah.
Now the idea of commutator is basically like if I act a B operator first and A operator, then it will get into some kind of state. Now later, if I act an A operator and later B operator, then it will morph into other state. Now these two end states are equal, then that means commutation is zero. And if it's not equal, then commutation is something, which we it is something. Now the fundamentally ideas are different. So what it mean to convert the relationship between these two dynamical variables into a commutation?
So
I was saying like I was a
in
bit confused idea.
yeah, in classical mechanics, we write down the Poisson bracket between the dynamical variable q and its corresponding conjugate momenta k, p subscript k, to be that turns out to be delta jk. In quantum theory, so the relation between Poisson bracket and commutation relation is as follows. It's just qj commutation is equal to I anti-commutation, Poisson bracket of Qj and Pk. That's it. This is in classical mechanics. We write down Poisson bracket, but when we are in quantum
So it is
mechanics, we deal with commutation relation instead of Poisson bracket.
so it is like not really we are not really connecting the ideas, but we are using the mathematical values to bridge between classical and quantum, right? Maybe can I think because ideas I find they are fundamentally different of a Poissonian and computation as per my understanding.
So, so Poisson bracket. Okay. So, what does commutation relation mean? So it means if you have any two operators, let's say A and B, and if they commute, then the order in which you measure A and B doesn't matter.
Won't matter.
If they do not commute, then the order matters. So that's what we do in so like x and px, that's I h cross. So it does matter the order in which you measure x and momenta along x, but x and py do commute, so it doesn't matter, right? But
Yep.
how Poisson bracket is defined? So x p Poisson bracket, the definition in classical mechanics is as follows. Let's say you have any two A and B. Poisson bracket is defined as this is the definition in classical mechanics. So when you have x and p Poisson bracket, it's let's say px. Okay. So when we are writing this xp, it means they are conjugate to each other. So that's implied. So it turns out to be 1.
Yeah, ma'am. Actually, I have understood mathematically. Like, okay, mathematics is quite easy. So I was just having trouble
And this
in
is
ideas.
how,
So that's why I was, okay.
yeah, this is how we relate the two. Yeah, maybe if I can come up with a better explanation, then I will let you know.
Okay.
Okay. Now this is also clear to you, right? You are asking why we are getting harmonic oscillators which are not talking to each other. This is done in momentum space, and as you can see, when you write down your Klein Gordon field in terms of the Fourier modes, you are actually having infinite number of harmonic oscillators for each momentum mode. So that's why when you obtain your Hamiltonian, you are having infinite number of harmonic oscillators, because harmonic oscillator, we know it's
Corresponding to each momentum, but not the each field, like the individual point at each field, right?
no, this is in momentum space. So corresponding to each momentum mode P, you have one harmonic oscillator.
Yeah, that's what. Yeah.
Yes, yes, yes. So usually harmonic oscillator we have A dagger A plus half, but here it turns out that you have delta function delta 0, which we neglect by saying that the ground state energy, even if it is infinite, doesn't matter, because experimentally we don't measure the ground state energy, but we only care about the energy difference. So that infinity we can neglect. Otherwise, we also had that term plus half a dagger, and the commutation relation between a and a dagger is 2 pi q delta 3 three-dimensional delta function p minus p prime. So when p and p prime are same, this is like a delta 3 is 0, which is infinite, but we can neglect that. Okay, so is this Hamiltonian expression clear to all of you? Like how we obtain this?
Yes, ma'am.
Or do you want me to go over it, like write down the field in terms of the creation and annihilation operators and then find out this Hamiltonian expression? Is it unclear to anyone? Okay.
It's clear, ma'am.
Okay, so what we can do then, we can do the same thing, but not for real Klein Gordon field, but for a complex Klein Gordon field. Okay, so if you remember, we actually considered a Lagrangian in terms of complex field psi in our first session. But now let's consider the complex Klein Gordon Lagrangian. So that is del mu phi star minus m square phi star phi. Okay. Now the question is, so the action is d4x del mu phi star minus m square phi star phi. So consider this Lagrangian. Okay, so for this Lagrangian, let us first, so the first part of this problem is to find out the equation of motion. So how do we do that? Someone?
We have Euler Lagrange. Okay.
Variation.
Sorry?
by variation of action.
Yeah, the Euler-Lagrange equation. But now since phi and phi star, so how would you do that? How many Euler-Lagrange equation will you obtain?
We'll be having two Euler Lagrange
Right.
equations.
So we can consider either phi and phi star to be independent, or you can, in an alternative way, you can also consider phi to be a plus ib, and then substitute it in your action. That will actually give you. So the action will turn out to be in terms of that real field A and B. So phi is complex, but A and B are real. So it will be m square A square plus another part. So here also you can obtain two Euler-Lagrange equation, but instead of that, let's consider phi and phi star to be independent. And then find out the Euler-Lagrange equation for each of them. So this is del mu phi star plus m square phi star equal to 0. Likewise you will get right. So there are two Euler-Lagrange equations corresponding to phi and phi star.
Ma'am,
Yeah.
with that action there will be I missing, right?
So the action that we considered earlier was a bit different. So that was not the complex Klein Gordon Lagrangian, but we considered a action. We wanted to consider a action which contains complex field. But this is the complex Klein Gordon Lagrangian. So if we write down
Yeah,
this, so this.
but if we consider phi as phi b, so if you decompose the action into like this A and B means there will be I missing in D4X, right?
Oh, I see. Oh, this is what you are saying. I see. Yeah. I guess you are correct.
Time?
Yeah, there will be I there. No, actually not.
No.
No.
No, actually, sir. Yeah.
Yes, yes.
Sorry.
There should be no I.
Yeah. Yeah, because action is always real. Sorry.
तो इतना चार होंगी ना?
Yes.
Yeah.
Yes, miss.
ये वाली चार तो इधर है इधर.
Ma'am, and actually I have some other doubt also. So, like whatever Lagrangian and Klein Gordon equations we are writing is for free particle under not any influence of potential. But like in real world there will be potentials also, and if you try to modify Klein Gordon equation,
There is
then
potential.
Lagrangian will be completely
No, wait,
different.
Wait. What you said? Let me first clarify that. So Lagrangian, you are saying there is no potential. I mean, it's del mu.
तेल में छोड़ दो डालो बता तेल में डालो.
M square, phi square. But this part is corresponding to the potential, right?
No, not that potential. What I was saying is like in Klein Gordon equation, because if we saw this and form an Euler Lagrange equation, that is basically Klein Gordon equation, and that Klein Gordon equation is for free particle, not a particle under a potential.
So here,
Right.
So far we are only considering.
No. Still the question is there. So what I was is like I was trying to derive the Klein Gordon equation under the influence of any potential. So I got one equation But the problem is, like, think of the potential will be frame dependent because it is dependent on space. So I'll give an
So
example. So
instead
think of if you
of,
have like,
yeah, sorry, go
so
ahead.
think of like you will be having some finite square well. So the end of length L of the shape, a proper length. Now, but in other frame of reference, it will be length contracted. That means the entire potential structure itself is length contracted. Now, if we try to formulate the Lagrangian of thing, then I think like it won't be, frame dependent. Sorry, it will be frame dependent. But right now, Lagrangian is frame independent, right? So, I think like, so is there any formalism for Lagrangian or for the field under potentials?
You are saying whether there is any constraint on the type of potential we can consider in quantum field theory.
Yeah.
So action is always Lorentz invariant. So yeah, if you consider a potential well kind of thing that you do in quantum mechanics, Garima, can you
आ जा
mute yourself?
अरे सर अंकल को बोल के जाना
Yeah. Yeah. What do I say? If you consider the potential well of a quantum mechanics and try to incorporate that in quantum field theory. Okay. First of all, here we are not dealing with a single particle. I mean, in the sense when we want quantum mechanics to be when you want to incorporate spatial relativity with quantum mechanics, we need multi-particles the way we have here. So a single particle in a potential well, I'm not sure whether that is a quantum field theory.
Wait. No. What I was saying is, like this Klein Gordon equations there, right? D amberts plus m square is, acting on the field or the wave function is giving zero. That's Klein Gordon equation, right? If you look at the derivation of the Klein Gordon equation, it is derived from the relativistic dispersion. E square is equals to p square plus c square plus m0 c square whole square. Now that is, now if you try to incorporate the potential in it under the influence of external potential, then E will be E minus V, and V is the potential term. Now if you try to push this energy and momentum in operators,
Sorry.
then you will be getting some different equation. Now the other idea which I was saying is, now here this potential term is there, right? V of R. Now V of R will be frame dependent. Why so? Because R itself is frame dependent, and to explain that I was giving this infinite square well.
Okay. I think I got your question. Okay, so the thing is, first of all, when we are doing quantum field theory, you remember how we are writing these fields? So from classical mechanics, if you had any coordinate x, I mean space-time coordinate x, so that actually gets in. I mean that actually. So let's write in, instead of calling it x, we write generalized coordinate. We wrote generalized coordinates, and that actually gets mapped to a field where position is a label. So it's not that you have something like x square here in your Lagrangian density. But you have phi which is being labeled by x. So your problem is in special relativity, when we do this boost transformation and so on, x, because of length contraction, x can become x prime, so the potential will get modified. How will the Lagrangian remain invariant? But we don't have anything like x square, like you don't have any position that way in your Lagrangian density and field theory. All you have is field, which are field at every space-time location x. So fields are being labeled by x. So that length contraction is not even coming here. Sorry, you are muted if you are saying anything.
So you are saying the field and space-time are independent, like at every space-time
So
a field is labeled?
yeah, so you think of space as a grid of lattice, the way we were saying first day, and then think of that at every location x you have a field. So at every location x in your space you have an excitation, which is this field phi.
But in that sense also still it must be dependent, because like you are writing the action and we are getting the Euler-Lagrange equation for a field, and that is basically a differential equation of depending on the variable space and time, a partial differential equation. And if we solve it, then the solution will be in terms of position and time. That means like this field is dependent on space time. So like I think like
Phi
we
can
can't.
transform, we will come back to all of this. If x transforms to x prime by a Lorentz transformation, let's call it lambda, then what will be the transformation of the field phi so that the Lagrangian remains invariant? All these things we will come back to. Boost and rotation we will deal with.
And the potential.
Yeah, the whole Lagrangian.
Yeah, under potential, like modified Klein Gordon.
Under the Lorentz transformation, how all these fields get transformed and the Lagrangian changes. So Lagrangian
Okay.
is like in classical mechanics, it's kinetic energy minus potential energy. So same is here.
Ma'am, I think I can answer this doubt.
Sorry.
I think I can clear this out.
Yeah, go ahead. You want to say something?
The space time, the whole history of particles and field depends. मतलब, the potential, any effect on particle will be depend on whole history of particle, or in other words the surrounding. So we do some modifications in Lagrangian so that the action is integrated over space-time. So inside the Lagrangian, which is known as Lagrangian density, is taken as to be at fixed space and time. In the sense the action which is action integrated over space-time. So inside integral we don't have to mention space-time individually, because we want a field equation such as here phi x, which is dependent on whole history of a particle. So that's why we taken action as integrated over space-time.
So basically, if a particle is, oh, you said like Lagrangian is dependent on history of particle, and when particle something collapses, then it changes the history of
No.
particle. I didn't actually.
Interaction, because the field created by initial particles which are another system, either it may be particle itself or surrounding. The whole history matters on interaction.
Actually understood the idea of Lagrangian depending on the history of particle, like what it.
I'm not sure, but so basically, how we got the Lagrangian, if you remember from the classical picture of a lattice, it was just the coordinates being mapped to a field phi. Instead of having discrete coordinates, like we can have, let's say, j equal to 1 up to n, these number of generalized coordinates. Instead of having those, we just mapped it to phi, but instead of having discrete number of generalized coordinates, meaning a finite number of degrees of freedom, you are now having an infinite number of degrees of freedom at every location x in space and time. So that is all that we did, and wrote down the Lagrangian in this particular form to get the Klein Gordon Lagrangian. So that was one picture, and probably he had some point, but I couldn't quite get by what he meant history of particles. What is? Can you unmute yourself and ask? Looking at chat box, it's a little difficult sometimes.
I was thinking that x, we call x a variable or label, but
Call X label. It's not.
it should be.
It's not like in. Sorry, there's an echo. Yeah, it's not like in quantum mechanics where X is your dynamical variable, which you make an operator to do the canonical to do the quantization. But here field phi itself is your dynamical variable, and at each location X in space and time you have one such excitation or field.
But mathematically, these variable and label are same. We can Taylor expand and about x
Sorry, I'm not sure.
we can do that. We can if we consider phi as a function and x as a variable, so we can do all that Taylor expansion required.
Okay, again, the way I was saying, don't think of phi to be a function of x. Then, I mean, x denotes a position coordinate where you have a field phi, the excitation. What I want to mean is x is not your dynamical variable, meaning you don't measure x, but instead you are dealing with dynamical variable which is phi, and at every location in space-time you have a field phi. You have a particular value of your field phi. Let's put it this way.
Yes.
So when the field is a real, so far we had been dealing with real Klein Gordon field Lagrangian. So at every location x you have a real number. But when we are dealing with complex Klein Gordon, when we will be dealing with complex Klein Gordon field, it's like at every space-time location you have a complex number associated with the field phi. Okay.
Yes.
So what we are doing? Okay. So we found out the equation of motion for a complex Klein Gordon field. Now the next thing that we want to do is let's find out the Hamiltonian. So in order to find out the Hamiltonian, what do you need to do? Because you
For field phi?
Uh-huh.
For field phi?
Yeah, I mean you have Lagrangian, you want to find out the Hamiltonian. What would you do?
Legendre transformation.
Yeah, so we do Legendre transformation, and for that we need to find out the conjugate momenta, right? So last time we saw that Hamiltonian in classical mechanics, which is like Q P dot minus L, that in field theory becomes the Hamiltonian density. So that is Q is phi, then the momentum, conjugate momentum is pi, so pi dot, what have I written, I'm so sorry, this is PQ dot, so phi dot minus L, okay. So the same thing we will do here. So our Lagrangian is minus m square phi star phi. So what will be the conjugate momenta? Conjugate momenta is del phi dot so this, if we write down, this is phi dot star minus gradient of phi dotted with gradient of phi star minus m square phi star phi. So del phi dot is nothing but phi dot star, and the conjugate momenta corresponding to field phi star is which is phi dot, right? So what will be the Hamiltonian density? Remember here phi and phi star are two independent fields. So Hamiltonian, so just like you sum over all the generalized coordinates, you need to take into consideration phi as well as phi star here. So the Hamiltonian, so if you don't do so, you will miss out one term of your Hamiltonian density. So it's very important that you keep this in mind. So phi dot phi plus phi dot star phi star minus the Lagrangian density, and Hamiltonian should be written in terms of the field phi and its conjugate momenta pi. So we will replace these in terms of pi and pi star. So we have pi star pi and then pi star minus the Lagrangian, again replacing phi dot by pi. So phi star is pi, sorry, pi dot is pi star and phi dot star is pi minus the other terms. So what you get is pi star pi plus gradient of phi dotted with gradient of phi star plus m square phi star phi. This is your Hamiltonian density, or the Hamiltonian is d4x sorry d3. Is this clear?
Ma'am, I have a doubt. Ma'am, what do you mean by saying that phi and phi star are independent? Phi star is complex conjugate of phi. So how do we get this that they are independent of each other? Are they different fields or
Yeah, so phi is complex conjugate of phi star, but actually, so just because, so that this confusion doesn't arise, I was telling you, you can consider phi, which is a complex field, in terms of A and B, which are two real fields. So you can see that the Lagrangian actually boils down to two pieces, or the action boils down to two pieces, one corresponding to your field, real field A, and another corresponding to real field B. So you actually get two Euler-Lagrange equations, one for A and another for B, if you consider this particular action and consider this decomposition of your field phi. So in that sense, yeah, there will be two Euler equations of motion corresponding to A and B, and the linear combination of A and B in this particular manner gives you phi. And phi star is actually complex conjugate of field phi, but the reason is that we need to consider these two to be independent, because they actually, I mean, if you write down in terms of A and B, you actually get two different fields, A and B. I mean, you actually get two different equations of motion for A and B. If thinking of, if I mean, if this thinking of A and phi star becomes confusing, you can always go back to real fields A and B, and you can write down the Lagrangian in terms of A and B. Sorry, I mean equation of motion.
Or one of the other way of doing this one is, like, even we can think that they are not independent on each other, and we can make del of phi star by del of phi as -1. If we do that, then wait, 1 star, sorry. So it will be basically 1, because if phi changes a bit, then it means that del of phi star also changes exactly in opposite in the same quantity. So the changes cancel and we will get 1. So even if we do that, we will get both the equations from single Euler-Lagrange equation. Actually, I tried that one.
Sorry, but can you repeat that again? You were saying take phi to be?
Yeah. No. Basically, like, we have Euler-Lagrange equation, right? So based on phi. Now, if we treat it as independent field, so like whatever phi star terms are there, like we are just keeping that one aside, and only we are differentiating everything on phi terms.
Yeah, that's what.
Now, what I'm saying is, yeah, but if we think of even though they are dependent, phi and phi star, now we won't separate the phi star terms outside. We will be using the biparts rule, and for del of phi star by del of phi, that will be 1. Why so? Because if think of, like, this is a plus ib and it has changed a bit, then a minus ib will be also changing in the same rate, or that bit only. So that will be giving 1. And if we do that, then we can get the two equations of motion from single Euler-Lagrange equation. And actually, I have tried this.
Yes.
Yep.
Ma'am, better just picture the two phi and phi star on a complex plane.
Sorry.
They'll give two perpendicular directions.
I mean, yeah, I mean, if you take variation of, I mean, if you go back to the way we derived the Euler-Lagrange equation, we varied field phi by phi plus delta phi. And if you vary this particular action S, delta of S, you are actually varying field phi as well as phi star. So from there, I mean, if you separate the surface term, you will actually get two Euler-Lagrange equations, one for phi and another for phi star. That is also another way of taking
But the mathematical way of thinking phi and phi star are independent means we can't make it like a phi plus b phi star is equal to 0. Like that we can't frame, right? That's what it means, right?
Phi plus phi, what did you say? Phi plus phi star equal to 0.
We can't make it in such equations. Simply we can't connect both phi and phi star to give 0. That's what dependency of two functions or two variables.
Sorry, if
Isn't
phi
it means
and
that?
phi star are complex conjugate of each other, then phi plus phi star will give us 2a, where a is a real field.
No, I'm saying alpha phi plus beta phi star is equal to 0. Like that, alpha and beta will be any arbitrary numbers. Like that, we can't frame it, right? If it is an independent variable.
Oh, okay. So,
then they both are really independent. Like that, is it mathematically? That's what they mean, like independent, right?
you can, okay, let me think how to answer this question. So you are saying mathematically when we say two things are independent, we basically get this kind of an equation where A and B are non-zero. Sorry, alpha beta are non-zero. But whether we can
Yes, ma'am.
so so yeah, so when because this is still can be done using this a plus ib and a minus ib, I believe. So in that sense, phi and pi star are actually independent.
Yeah, that's what I'm saying. Is it mathematically? Is it right? What I'm telling?
Yeah, I think so.
Yeah. Okay then. Okay.
Okay, so once we have the Hamiltonian, now we want to do the quantization. So the similar thing that you have already done, but here we need to quantize field phi as well as phi star. That's the only difference. And ultimately the Hamiltonian, as you will see, will turn out to depend on two types of creation and annihilation operators. So that's what we are going to see. So here then let's promote our dynamical variable phi to an operator, but we will still write phi, not care about putting hat on it. But we will be working with Schrodinger picture, so where operators do not depend on time as of now, but as we go on we will get back to Hamiltonian picture where operators will depend on time. So phi of x commutation relation with its conjugate momentum pi is equal to I delta 3. So once you promote phi to be an operator and pi to be the operator conjugate to field phi, as well as phi star to an operator phi star and phi star to be the operator pi hat star, then you can write down this canonical commutation relation just like in quantum mechanics, but instead of getting Kronecker delta, you now have three-dimensional delta function because phi and pi both are labeled by the space-time coordinate x and y. Likewise, phi star and pi star is also I delta 3 x minus y. So that is the canonical commutation relation. Now, so then what do we do? We can, so remember in simple harmonic oscillator of quantum mechanics, what do? Your dynamical variables there are x and p. When you promote them to operators, you can write x in terms of creation annihilation operators, right? 1 over square root 2 omega a plus a dagger, and you write momentum as minus I square root omega over 2 a minus a dagger. This is what you do. Now we saw that when you write down field phi, that becomes, you can unmute yourself and say, Abhinav.
No, like not to me. So one guy asked like why there's no hedge cut. So I
Oh,
was
okay,
just
okay. So
answering.
yeah, the convention is h cross equal to c equal to 1 we are taking. So this is what you do in simple harmonic oscillator, and we have seen that when you write down your field phi in Fourier modes, the Hamiltonian, the Klein Gordon equation actually boils down to that of the equation of motion of a simple harmonic oscillator, but for each momentum mode p. So that's what we are going to use. So we are using the same, we will be using the same trick that of a simple harmonic oscillator, well known to us from quantum mechanics, in order to quantize this complex Klein Gordon field. So we write down phi of x as integration d3p over 2 pi q 1 over 2 omega p a uh, corresponding to momentum p exponential I p dot x plus, so there's a big difference from what you knew before, but these things are necessary in order for this commutation relation to be true. So this is what we saw actually last time, but I did it hurriedly. Some of you said it was not very clear at the end. So today maybe we can do it for the complex Klein Gordon field again. It will become clear, I think, to those for yeah.
Why we are taking this particular form of phi x? Like
Yeah,
this,
this is what I was saying. So, okay, so you do this thing, xp, and in simple harmonic oscillator, and xp commutator is IH cross. Then you figure out that the commutation relation satisfied by A and A dagger is just 1. So, okay, so what I have written is for real Klein Gordon field, okay? Here it will be different, and why that will be different I'll tell you. So this is for when you have real Klein Gordon field, real KG field. So this is what you know from the lectures, I believe.
Ma'am, you are putting vector signs on axis.
Yes.
So does that mean we are not working in four vector formalism?
Exactly, this is what I was telling you. So as of now, we will be working with Schrodinger picture. In Schrodinger picture, the wave function depend on time, but operators do not depend on time. So we have already promoted our dynamical variables, phi to operator phi hat. So 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 this means what we are writing here is an operator.
And the argument
And,
x.
and the point is we are in working with Schrodinger picture, that's why field phi is independent of time t as of now, but as we will go on, field phi we will write as x and t, and how that will change things we will see, we'll describe. Is there any delay, I mean when I'm scrolling, are you facing any issue?
Yes,
I see.
a little.
Yeah.
There's a small delay.
Okay. I'm sorry. Yeah, the bandwidth. Okay. So okay. So this is for real Klein Gordon field. So this. I believe you all are familiar with this. Are you? So you have used this field, found out the conjugate momenta corresponding to this field, and obtained that Hamiltonian, right? Is that correct? Okay.
yes.
Okay, so now, so the point here is this field phi is actually, so this is now operator. This operator is actually Hermitian operator because phi is a real number. So that's why you have A here and A dagger here, which are complex conjugate of each other. So if you take phi dagger, you will get back phi. But now we are dealing with complex Klein Gordon field where phi is not a real number but a complex number. So the operator is not Hermitian. So that means for a complex Klein Gordon field, we need to consider two different operators instead of just one. So what we do is, plus some other operator, call it B, right? Okay. And just like in quantum mechanics, A dagger satisfy identity, here AP and A dagger P prime, they satisfy this particular relation in order for this canonical commutation relation to hold. Okay, Just like here, this is consistent with this. Here also, this particular commutation relation between your creation and annihilation operators are consistent with, has to be consistent with this canonical commutation relation between your dynamical variables, which are now operators, of course. Okay, so that is field phi. Now the question is, what will be the, so for real Klein Gordon field, pi was, let me write down so that you recall what you already know. So pi was T3p over 2, just like here in simple harmonic oscillator, it's A minus A dagger. It was this. Now what will be the conjugate momentum pi, so that okay, so here for real Klein Gordon field, we only had one set of creation and annihilation operator, that is AP and AP dagger. So that's why we wrote down this commutation relation between AP and AP dagger. But now for complex Klein Gordon field, as we said, field phi is a complex number, so that's why your operator cannot be Hermitian, it is non-Hermitian, and that's why you need two such sets. So that means you now have AP prime equal to 2 pi q delta 3 p minus p prime, and similar commutation relation for the other set of creation and annihilation operators. Now, assuming this to be the case, and you also need canonical commutation to be true, the conjugate momentum has to be something like AP dagger exponential Now let's verify whether this is giving us correct commutation relation or not. Okay, so let's find out what is the commutation relation between phi x and pi y. So our expectation is this should give I delta 3x minus y, and let's verify whether using these two we are getting this particular right hand side or not. Okay, so that way you will be familiar with you will be familiarized with the computation, the thing we did last time hurriedly. So let's do that, and please interrupt me at any intermediate point if you are not following anything. Okay, so sorry for scrolling up and down. Yeah, so why there is always 2 pi in commutation relation involving A? Is it convention? Yeah, so this is what I'm saying. So unlike quantum mechanics, where we just had 1, we now need this factor of 2 pi cube, because we are doing a momentum Fourier integral where we also have this 2 pi cube, so that this 2 pi cube ultimately gets cancelled out and you get this commutation relation of phi and pi. That's why that 2 pi cube is necessary in the commutation relation between the creation and annihilation operator. Okay. So let's see how that actually helps us to get this particular thing. Okay. So what we are doing is calculating the commutation relation between phi and pi. So d3p, and it doesn't make sense to use same integration variable, right, when you have two different integrations. So we write d3p prime and 2 pi to the power 6. There is I in front, let's keep that outside. Square root of omega p prime divided by omega p. Let me know if you can't follow anything. Okay. Then and what do we have? Commutation relation. AP exponential I p dot x plus exponential of minus I p dot x, comma a p prime dagger okay. So we just wrote down these two factors, but p replaced by p prime in case of pi, and also x replaced by y because we are taking phi of x and phi of y commutation. Okay, so then we have four terms, but as you know, the commutation relation between A and B is always 0 because they don't talk to each other. d3p prime. So we will basically get two terms. AP prime dagger exponential of I p dotted with x minus p prime dotted with y. Another term is the commutation relation between this and that. So plus comma, so there is a minus sign here, so let's keep that outside. B p prime exponential of I minus I p dot x minus p prime dot y. Okay, and yeah, so these are the two terms, and so now we will use these two relations here and here, so that will give us I d3p. So 1 2 pi cube will get cancelled out because of the 2 pi cube present in this commutation, and we are left with 1 over 2 pi cube here, square root of omega p prime omega p. We get a delta 3 p minus p prime exponential of exponential of I p dot x minus p prime dot y. But here, see, it is the other way around, right? It's b dagger b, so there will be another minus sign coming from this commutation, and we will get plus Is this clear? If it is not clear, let me know. Now we are doing the p prime integration. So everywhere p prime will get replaced by p. So this is equal to I integration d3p divided by 2 pi q half. So p prime, when it is getting replaced by p, these two, this is giving us 1, and we have exponential of I p dot x minus y plus exponential of minus I p dot x minus y. Okay. But now the point is, in this second term you can replace p by minus p. How you can do that? So p is a vector, right? If you replace p by minus p, this measure will also get a minus sign, but then there is integration limit also from minus infinity to plus infinity. So when you replace p by minus p in the second term, that integration limit will get reversed from plus infinity and minus infinity, and this minus sign that you are getting from this measure, that you can use to change this integration limit back to minus infinity to plus infinity. So that's why when you replace p by minus p in the second term, you exactly get back the first term. So this is
Just tell it again, please.
okay. So I'm saying, suppose you have just not d3p, let's say just a single d of, let's say, some, no, that's a bad notation. Let's say dp, okay, exponential minus I p x minus y, where these are not vectors, anything, just numbers. So minus infinity to plus infinity. Now let's say you are writing dummy variable, so p is equal to, let's say, minus p prime. Okay, so integration limit for p, if it is from minus infinity to plus infinity, for p prime it will become, so dp will become minus dp prime, integration limit becomes plus infinity to minus infinity, and here you get I p prime x minus y. So this is what? This is dp prime minus infinity to plus infinity exponential I p prime x minus y. Right? So if we do the same trick for this 3 vector p, you will get a minus sign here, but then the integration limit will be reversed. It was from minus infinity to plus infinity, but when you do that change in sign, it will become plus infinity to minus infinity. But then you can use this extra minus sign that you obtained to change this integration limit back to minus infinity to plus infinity, the way we did here. So what will happen is, this term will become identical to this first term. Was it clear now?
Yes, ma'am.
So this is equal to I d3p over 2 pi q, that half will go away. We have exponential I p dot x minus y, and this is nothing but definition of Dirac delta. Okay, so this is what we wanted to show. So that means what we considered, the field phi and pi are the correct expressions in terms of creation and annihilation operators. Okay. So the next thing that we can do is find out what is the corresponding Hamiltonian. Okay. So Hamiltonian we already found out for the complex field, complex Klein Gordon field. Now what we need to do is, so now we also have phi written in terms of the creation annihilation operator, also pi. So we need to use those things in this expression and then find out the Hamiltonian in terms of the creation annihilation operators. Okay. So let us do that. So this analysis that we have done for the commutation relation, was it completely clear to all of you? Because these things will come back again and again, so you should be familiar with this. I mean, comfortable with this. I mean, okay. So let's find out the Hamiltonian. Was there anything else that was taught in the last week apart from the quantization of a real Klein Gordon field? Any other topic was it covered? Any other topic apart from the quantization of a real Klein Gordon field? So we are now doing quantization of complex Klein Gordon field.
Do you mean week 2?
No, week 3 probably you have watched, haven't you?
Yeah, just one lecture is pending. But
But week 3 lectures were completely
Quantize-
on quantization.
Yes, ma'am. Just quantization, ma'am.
Okay, so today we will only do the quantization of the, so this Hamiltonian we will find out, and then maybe we can stop, and then next week whatever you learn, based on that we will decide what to cover here.
and also, like, while before leaving, can we just talk about some insights on Noether's theorem? Again, not the mathematical part, but physical intuition part.
Sure. But let us find out the Hamiltonian, and then we can.
Yeah, first we'll finish this.
Yes. Okay. Sure. So d3x. So I'm writing down the expression of the Hamiltonian. Okay. So let us find out each of these terms separately. So pi star pi d3x again, interrupt me if anything is unclear in between. So d3p prime. Now we are taking a product, okay, not a commutation or anything, but we are taking product of, both are at same x. So let me go back to the definition. Okay, so that's the definition. So d3p. So okay, so when we are taking pi star, so let me so this is pi, and pi star is d3p minus I square root omega p exponential of I p dot x minus exponential minus I p dot x. Okay, so these two things we are replacing there. Okay, so this is equal to multiplication of I minus I, that will be just 1, and we have half in the denominator, square root omega p prime times a p prime dagger exponential minus I p prime dot x okay. So then you get 4 terms here. Sorry, this is a bit lengthy. So since these are operators, you shouldn't change the order. Plus exponential of minus I p plus p prime plus b dagger b p prime exponential minus I p minus p prime dotted with x. Okay. Now what we will do is, so we have d3x exponential of I p minus p prime dotted with x, and what is that? That is 2 pi cube, then 3-dimensional delta function p minus p prime. This is what we used while finding out the commutation as well. So therefore this becomes divided by 2 pi to the 6. Okay, let me copy that. Okay, now we are replacing all these by delta functions. So this will be delta of p minus p prime this will be delta of p plus p prime p prime, and again but this 2 pi cube will cancel with this and give you 2 pi to the 3. Okay, it's clear so far. So now let's yeah, someone has
I have a doubt, like when pi and pi were variables, we could multiply it in any order. But like if we multiplied in other order, like what we have done in here, other order, then the order of operators, when we converted the variables to operator, would be changed, I think. So, like there might be multiple expressions for same
yeah, so
operator.
I mean you can start with pi star, but then you should stick with that order. So once you take pi star pi all or pi star, you should multiply all the operators in, I mean, so when you are writing pi star pi, you shouldn't just flip the order.
Like if in the
You
starting
could have,
I write
no, you could
pi
have
star and
started, yeah, you could have
then
started
did all this same thing,
Mhm.
then the answer will be same. Like it is written, what you have got here, like it will be same. Like if I do it pi star
Well, pi and
multiply
pi
and
star.
then
Okay, wait. So pi and pi star, these two are independent of each other. So the commutation relation between pi and pi star is 0. So which means pi star is same as pi star pi. So you could have started with pi star pi here. Sorry, pi star here.
but it makes difference when we like put operators in place of pi. Like functions commute like but operators
Yeah,
like when
I'm
we
saying
put
the
in
same thing.
this.
Operator pi and operator pi star, these two are independent. So the commutation relation, if you remember, that we wrote down here, is between phi and pi and phi star and pi star. Only these two things do not commute with each other. But phi star with phi, they commute. Again pi star, they commute. So it doesn't matter which order you write the Hamiltonian. But once you write down pi star pi, and there you have a dagger, right? So you shouldn't flip, because a dagger do not commute. They satisfy this particular commutation relation. So this is not equal to 0.
So like answer will be same. Like if I do first pi and pi
Yeah,
star
answer
and
will be the same. You can
like
check. You can check.
this.
Because if you
So, but like if pi is the function, then it is pi star. But if it is operator, then it should be dagger.
exactly.
Like
Well, yes. These things should be replaced by dagger when we are finding out the Hamiltonian operator. Yeah. Yeah, because on the right hand side we are anyway writing dagger. Like we took the complex conjugate, I mean Hermitian conjugate basically. So that's why AP dagger got converted to AP, BP dagger got converted to BP dagger. Okay. So far I think the steps are clear. Now we are taking the P prime integration like before. So, okay. Uh, A dagger. So P prime is becoming P here. For the second term, P prime will be replaced by minus P. So A dagger minus P. P prime getting replaced by minus P. Okay. Now for this omega P, this is nothing but mod of P square plus M square. So P becoming minus P won't affect it. So you have omega P outside by 2. Okay. So these 4 terms we have obtained for the first term of the Hamiltonian. Now let's find out the second term. What was the second term of the Hamiltonian? It was gradient of phi dagger dotted with gradient phi d3x. So let's recall what was the definition of phi. Phi of x was integration d3p over 2 pi cube 1 over 2 omega p exponential of minus I p dot x plus exponential I p dot x, right? So gradient of phi would be what? d3p this will give minus I p plus exponential I p dot x. Okay. So that's gradient of phi. So let's write IP outside maybe. So gradient of phi dagger would be d3p over 2 pi q minus I p okay. So now let's find out. This is equal to 2 pi to the power 6 1 over 2 square root of omega p prime, again minus I and I giving us 1, so p prime dotted with p minus ap dagger exponential, sorry, did I write something wrong? It was plus right here, let me just check, sorry, it was plus for the first term. So in the middle of the computation we shouldn't change the convention. That's plus, that's minus, so here it becomes minus and that becomes plus. Minus I p dot x yeah, minus a p prime dot x okay. So again we need to multiply, we will get 4 terms and then use the property of delta function. So what are the 4 terms? It's a dagger, so it will become plus ap prime minus I p minus p prime dotted with x minus minus exponential I p plus p prime dot x the last term. Okay, so now we'll be replacing these by the delta functions. So this becomes delta of same trick that we used.
Ma'am, actually, this is extremely lengthy. Like, is there is any more shortcuts kind of thing?
I don't think so. I mean, once you learn, you do it once, and that's all. Then you don't need to do it again and again. But when you learn quantum field theory, you should know this computation because these things will come back again and again.
Like, ideas are okay.
Yeah.
Like, not completely. But yeah, I can understand what he's doing, but
Yeah.
mathematics
But yeah,
is
it's
extremely
lengthy.
lengthy.
Yeah, it's lengthy.
And in fact, it's hard to stop my sleep.
So, again, we are taking p prime integration. So, and omega p and p prime doesn't matter. Under p going to p prime, it will remain same. So we get 1/2 omega p outside. This is p square. I think whatever problem we do in this course will be lengthy. For the second term, p is p prime getting replaced by minus p. So again, p square minus p, okay, plus p square ap dagger yeah, okay. So this we got from the second term. Now since this is getting really lengthy, last term I'll just write and you can just do it for yourself. Homework. Phi dagger phi. So that's the last term. Please do it, okay, by yourself. Let me see my notes. I'll not derive it because it will take more time. So the last term is d3p over 2 pi q 1 over 2 omega p a dagger p ap minus p okay. Now all we need to do is combine all these three terms. So remember the Hamiltonian d3x this is equal to okay, so just let me copy that first term so that you can see what's happening ultimately. So it's gradient of, okay, so now we are writing Hamiltonian operator plotted with gradient of phi, that is equal to that, and the first term was so that was pi star pi. Okay, so now if we combine these three, what do we get? We need to multiply by m square here. So m square. Okay. So you can see that. Okay, just. So this is d3p divided by 2 pi q. Half, let's take outside, and what we get is, so from this, and so see here it's, so there is p square here, okay, in this term, and m square here, and so that will give us, when you add this term with this term, that will give you omega p square in the numerator. That omega p square will get cancelled out with this omega p, will give you 1 omega p in the numerator. So basically, I don't know, was it clear? Just let me know if it is not. So it's, you will get omega p, and then these terms from these two things will get cancelled out with these terms. So that will get cancelled out with these two, and what we will be left with is AP dagger plus AP dagger AP plus B dagger B dagger. Okay. So someone was saying, no, if you take the order other way around, so you will get the same thing. I mean, because from one term you are getting a dagger, from another term you are getting a dagger a. So it will be that from one term you are getting a dagger a, another you are getting a dagger. So ultimately the order in which you are taking pi star, that won't matter. Okay, and so the thing that we now need to do is write down this as, so this is what, this is half d3p over 2 pi q omega p to a dagger a plus 2 b dagger b plus that delta function, sorry, the commutation, so a dagger plus b dagger. Okay, and these are again delta 3 0, which are actually infinite but doesn't matter, so we can neglect them and write the Hamiltonian as a dagger a plus b dagger b. Okay, so the exact same thing you had for real Klein Gordon field, but now you have two kinds of particles, like one created by the creation operator a dagger, another created by the creation operator b dagger. That's the only difference. So we are done with the computation. To all those who are sleeping, please wake up. Okay, now, yeah, Abhinav, you had some question related to Noether's theorem. Yeah, before we go to that, anyone having any issue on this, what we did. Please ask me to repeat now, I can repeat, but later on you should be comfortable with this. Okay, so no one is saying anything, you can go ahead.
Excuse me, ma'am.
Yes, yes.
Can you explain what is the physical significance of Fourier transformations in quantum field theory?
So by doing Fourier transformation, we write position space, functions in position space in terms of functions in momentum space.
Okay.
Yeah. I mean, that's the usual thing that we do everywhere, not specific to quantum field theory.
Okay. Thank you.
Okay, any other questions?
Why the variable p is interpreted as a momentum in Fourier when we do Fourier transform?
Yeah, because that's what we do, right? In Fourier position in momentum space. Huh?
Uh, like this variable p is like if like it is coming from the single dimension quantum mechanics, like if you take a
Here P is
wave
also
function, Fourier transform of wave function of position, in terms of position, it is written wave function. Then if you take Fourier transform with respect to variable,
sorry, first of all, phi is not a wave function. You shouldn't confuse with wave function. Phi is just a field. It has no probability interpretation. It is not a wave
ma'am,
function.
I am asking why if we do Fourier transform of this,
So okay. So first of
then
all,
why variable p is interpreted as momentum?
so we are taking Fourier transform in order to write a field phi which is in variable x in terms of a field phi in momentum space. I mean, that's what Fourier transform we usually do. I don't know how to answer this question any better. Anyone has any?
Ma'am, I am asking why the x, I know like it is like position and time denoting, but like if p is a variable name, that but this variable name correspond to like physically like momentum, how
No,
it
just like x is also the label here for field phi. Okay, so at every position x you have a field phi, and that field you can express in terms of a field which is being labeled by the corresponding momentum p when you go to this Fourier transform. When you do this Fourier transform, I'm not sure if I'm answering your question. So first of all, why we had to do that? Because we saw in Fourier space, so if we write phi in terms of this, this Fourier modes, and then replace this entire thing in this Klein Gordon equation, so what will happen? This is del mu, this will hit this exponential, right? It has nothing to do with this. Sorry, here the first term will hit only this. So what I mean is, so del mu is del 2 del t2 minus grad square. So when this hits this term, we get just del 2 del t2 acting on phi, and when this grad square hits this phi, it will hit only this particular exponential, and that gives this mod p square here. And then we said that the Fourier mode is actually satisfying an equation of motion which is identical to that of a simple harmonic oscillator. And we went on to get onto this Fourier transformation business because we wanted to quantize our Hamiltonian. And how do we do that? A very useful trick is that what we already know, exploit that. So we already know how to quantize simple harmonic oscillator. Going to Fourier basis, we can see that the field phi in Fourier in terms of this momentum p, which are the Fourier components corresponding to field phi, are actually satisfying what we already know. I mean, whose quantization we already know. So that helped us to do this quantization, write phi in terms of creation and annihilation operators, the way we do for a simple harmonic oscillator.
It is called like momentum for like it is satisfying any particular like SHM equation like dispersion type of thing, like the variable p. So that's why we are calling it momentum. Like I am thinking like if we get any function
Oh, I
of
see,
position,
I see.
like
So
and if we do Fourier transform of it,
from
so
this equation,
but
from this equation, it's clear that it has to be the variable p. Okay, you are saying it's a dummy variable. Why call it momentum? That's
yes, I was
okay. So
yes
it's
I
a
was
dummy
saying that.
variable. Why call it momentum? But if you give it momentum interpretation, then it boils down to that of a simple harmonic oscillator equation of motion. Yes. Yeah, good question. Any other questions? Okay, so let's come back to Noether's theorem. What questions you had?
Yeah. So mathematically part, I have understood Noether's theorem. Like you are just basically changing the Lagrangian in certain way and plugging it into action, varying the action, and getting the continuity equation. That's okay. But like physical intuitive part of Noether's theorem, because like we are changing Lagrangian in form of del mu g mu. Now, like how to interpret that physical change of Lagrangian as del mu g mu? Like is it kind of a rotational kind of thing or translational kind of thing? And in fact, how the structure of del mu g mu is giving this symmetrical transformation.
So okay. First of all, we are changing the Lagrangian by del mu g mu purposefully because we saw that when the Lagrangian changes by a total derivative, then the equation of motion remain invariant. So this change del mu g mu is by purpose we are doing so that the equation of motion remain invariant. Okay. Now you are saying how to interpret this physically. So this was most general. So field phi changing by some amount delta phi. Then to understand it physically, we went back to a specific transformation, space-time translation, which are nothing but the Lorentz transformations that we do. So they are also space. There is rotation and a boost. This is one sort of that kind of a translation, but we'll come back to those Lorentz transformations later on. But this is one thing that is happening physically, like space-time translation. So time changing by some epsilon 0, spaces are changing by some psi 1, psi 2, psi 3. And if you do that, you can see that the Lagrangian is changing by some g mu, which is like xi mu L. And then we obtain the conserved current and corresponding conserved quantities. And we know that quantity corresponding to time translation is energy, conserved quantity corresponding to translation in space is momentum. So we obtained T00 and then we saw that T00 also matches with the Hamiltonian that we obtained for real Klein Gordon field.
Yeah, that's okay. No, I was saying like the translation of del mu g mu is a generalized form of any symmetric transformation, right? A generalized symmetric transformation.
No. Del mu g mu is just any. So G mu is any function. So Lagrangian is changing by a total derivative. That's all it means. By a total derivative. So when you write down the action, it's d4x acting on the d4x, then the Lagrangian density. So this del mu G mu will give you a surface term. So that's why we are writing a total derivative of anything.
So del mu G mu don't capture any symmetrical arguments?
By
Because I thought.
Okay, here by symmetry we meant this, that any transformation, there is any I think a delay. Okay, so by symmetry here we meant any transformation that will keep your equation of motion unchanged. So for the equation of motion to remain unchanged, your action should remain unchanged under that transformation. And if your Lagrangian density changes by total derivative, if it doesn't change, anyway your action is invariant. But if it changes by total derivative, let's say, the action will still remain invariant, because we said that the surface terms we take to 0. So that is a general thing that can happen to the Lagrangian, but that will still be a symmetry of your theory, because with this transformation of the Lagrangian, if you change your field phi, your equation of motion will remain invariant. That's what we meant by symmetry here. Is it getting clear?
Oh, wait.
By symmetry, we are not trying to mean any symmetry argument being incorporated in G, but we are just trying to mean that your equation of motion that you had, that shouldn't change.
Oh, okay. So can I think in this way, like if phi changed to phi plus del phi, then Lagrangian will be changing in a structure of Lagrangian density, like the change in Lagrangian will be in the form of del mu G mu.
Yes, that's what we are writing here. So delta L, the change we are replacing by that del mu G mu. That is the most general thing that can happen.
Then I think this
equate to this G is 0. It may happen that this G is 0. For example, that complex Klein Gordon field. Let me just tell you one example. So Lagrangian was del mu phi star del mu phi minus m square phi star phi, right? Let's say we are changing field phi to I alpha phi, where alpha is a constant. Okay? Then the Lagrangian density will remain same, because minus exponential minus I alpha will come from phi star and exponential I alpha will come from phi, and those two will cancel.
Cancels out.
Yes. So for this particular transformation, then the G mu that we wrote is actually 0.
And other thing is not a question but a kind of problem, like I was continuously facing while studying, is like like I am ending more confused than how I started, because think of I'll give you an example. So think of we will be saying a commutation relation of A and A dagger is equals to 1, right? And we have done that and we have proved it very well. But if you think what exactly it means, is a think of you have nth energy level, and we have increased by a ladder up operator and again decreased. So again we'll get back to nth energy level. When we measure, we'll get some value of energy. Again now when we decrease and again increase by ladder up operator, we'll get some other energy value. So when we think intuitively, we will be thinking because as we are getting in the same state back, then the energy values must be equal. But that's not the case, because we know the energy will be h bar omega difference. So it's you will be confused Fundamentally, and if you talk about mathematics, yeah, I have done the mathematics many times, and I myself proved, the commutation of A and A dagger is equals to 1. But and this is just one example, but thinking physically, in some sense, it's just confusing and getting a vague concept of everything.
I probably didn't get your confusion.
Oh, that's unfortunate. Wait. So think of like
Yeah, maybe
you have.
maybe you can share your screen and then write it what you want me, if you can. You are saying A dagger, you are changing energy, increasing.
No. Basically, I was trying to explain the commutation of A and A dagger is equals to 1, and I was saying that we all derived that mathematically. That's okay. But when we think of physically that this commutation relation of A and A dagger being 1, I was trying to explain what it really mean to physically understand this commutation is equals to 1. And that's what I was trying to explain. So, and if you think physically, it really makes no sense. Because think of like you have nth energy level state. Now you have applied A dagger, which made it into n plus 1th energy state, and again annihilation operator and made into nth energy state back. That means like A dagger. Right now, when you measure it, you will get some energy value. Keep in back of your mind. Now you are acting a annihilation operator A, which is making it to n minus 1 state, and again making up back to n state. Now you will be getting some other energy level and other energy. So if we think physically through some common sense, like we will be thinking like these energy levels must be equal because the ending is same nth energy state. But we have proved mathematically that if we measure the energy, then it will be like h bar omega difference. That's what I was trying to. And I have done mathematically many times, like proving the Hamilton acting on A dagger, commutation of A dagger is h bar omega.
Yes.
Did I?
Sorry. A dagger is
Got.
1.
Yeah, but physically it's just not exactly making sense. That's what I was saying, like how to tackle this.
I'm still not sure because in my mind everything is perfectly fine here. Probably that's why I'm not able to. I'm not sure.
Okay, fine. I'll brainstorm myself and I'll think about it.
Let me try to phrase your question. So, you are in nth excited state, and energy corresponding to that state will be h cross omega.
Some energy level.
Yes.
Okay.
That is exactly what it is, I guess. Now you are in n plus 1th energy eigen state. So the energy corresponding to that will be n plus 1 plus half h cross omega. Now you are saying the energy difference En plus 1 minus En will be h cross omega. Yeah.
No, not that. Yeah, that is okay. That's intuitive. No, what I'm saying is, I don't have pen. Just a minute. Sorry for delay, but just a minute. Just a minute.
Should I stop sharing?
or otherwise, like I will ask this question next time whenever I have drawn everything.
Okay.
So
That's
that
good.
it's
Yeah, that's good. Sounds good.
yeah, but that's not the question I was asking actually.
Okay.
Yeah.
Okay, let me know next time again. Thank you.
Thank you, ma'am.
Ma'am, can you share the Google Drive link where you post the class notes?
Is it not shared in the NPTEL portal?
I couldn't
No,
find
ma'am.
it.
Is it?
No, in the comment box it's not start.
It's not there anywhere. It's strange.
Actually, I'm about to ask when you are going to share the class notes and then the videos.
Just a moment. Just a moment. I think this is the spreadsheet link. Yeah. Oh God, what did I do? Sorry. Just 1 minute. Okay, I'll just share it. Let me know. Can you access this? Okay. Fine. So let's meet next week. Thanks again.
Thank you, ma'am.
Yeah.
Thank you, ma'am.